Okay, so Module 3 time, we're going to be dealing with Module Chapter 3 again, the second half of Chapter 3. And this is all about moon phases. And I want you to, first of all, before we start anything, ask yourself, why are there moon phases? What do the different moon phases look like? And why do we have them? And are they visible all the time? Do you see all the moon phases, or do you only see a few of them? Do you ever notice the moon being up in the sky during the day? Why is that? Ask yourself those questions really honestly. Try to answer that before we get into the material, because and what you should find is that it's very closely tied into Module 2's topic. Remember, Module 2's topic was essentially, why are there seasons? Why is it hot in the summertime? Why is it cold in the wintertime? And hopefully we came to the conclusion that it's not proximity, right? That's the easy, that's what a lot of folks would answer. And it turns out to not be the correct answer. It's a misconception. Same thing with moon phases. There's a lot of misconceptions about moon phases, why the moon takes on different shapes during the course of the month. So I want you to honestly ask yourself the question, why are there different moon phases? What do they look like? When do we see them, et cetera, et cetera? And hopefully by the end of this module, you'll have some pretty solid answers. And if nothing else, you'll be able to answer. Now, first of all, do you recognize this book? This is a book that all my children have really enjoyed called Go Dog Go. And inside the book, there's a couple of illustrations. This is a nighttime scene of some dogs going to sleep. And then on the next page, it's a daytime scene of those same dogs waking up in the morning. And turns out there's some very interesting conclusions we can draw from those illustrations, and it has to do with moon phases. So I hopefully you pick up some really interesting information in this module. Okay, so do you know the basic terminology about moon phases? Well, first of all, the new moon. New moon is when the unilluminated side of the moon is facing the Earth. So we really don't see the new moon, and so that's what in this little simulation you don't see the moon's face lit up whatsoever. Now, here's waxing crescent. Okay, it's called a crescent moon because it's less than halfway lit up, but it's not not illuminated. There's some part of the moon that is illuminated, just not half of it. So it's called a crescent phase. The moon is in its quarter phase when half of the side that's facing the Earth is lit up. Gibbous is when you're more than halfway lit up, but you're not fully lit up. Full obviously is when the entire illuminated side of the moon is facing the Earth. Here's another gibbous phase. Remember, gibbous is when it's more than halfway lit up, but not fully lit up. Here's another quarter phase. Remember, quarter is when it's halfway illuminated, but not, that's it, just halfway illuminated. And then crescent is when, oops, that part of my simulation seems to have paused. That's interesting. There we go. Waning crescent phase, again, is when it's less than halfway lit up. Now notice that we've got these different words, right? Waning and waxing. What does that mean? Well, waxing is when the right side is lit up. So as it's getting from day to day, the moon will become more and more illuminated. That's what we call waxing, in this case, waxing crescent. Eventually, the right side of the moon will be lit up when viewed from Earth. That's called first quarter. Waxing gibbous, again, it's going to get more and more lit up with each passing day until eventually it gets to full moon. Now notice in the waning phases, it gets dark. The moon gets dark from day to day on the right side. So you really always have to pay attention to the right side of the moon to decide whether it's waxing or waning. Last quarter is when the right side is dark and the left side is lit up, and then waning crescent, again, is when the right side is dark and left side is lit up. And we can actually just allow this to go over the course of essentially a month. So we got waning crescent for about 7 days until we get to first quarter. Another essentially 7 days we're going through waxing gibbous until we get to full moon. Now we get into the waning phases. Once we pass full moon, we get into waning gibbous, still more than halfway lit up. Now we get to last quarter, or third quarter, and then finally we get into waning crescent. And if you're still having a hard time understanding the moon phases, have I got a great idea for you. And all you need is a light bulb, a pencil, and a ping pong ball. This activity is actually described in your textbook on page 793, the first two think and do questions. And the important thing for this activity is that you create a light source in a corner of the room. So I suggest putting a lamp in your doorway or in a corner. That will act as your only light source for this activity. It will be the sun. Once you have your light in place, put it at the end of in the corner of a room. And what you do is you take your ping pong ball and pencil and you face the light. And you want to put the pencil and ping pong ball at an outstretched arm length. One thing that I advise you to do is to hold the ball a little bit above your line of sight, so you don't block the light with your ping pong ball. If you do that, that's an eclipse, and that really doesn't show the moon phases that we're trying to learn. So put it a little bit above, and again, try to shade your eyes for the time being, but see how much of the side of the ball that is facing you is illuminated by the light. Once you've gotten that established, slowly start to rotate yourself counterclockwise as viewed from above. So essentially you'll be turning toward the left. So rotate yourself very slowly, and again, keep an eye on your ping pong ball. See how much of the face that is facing you is illuminated. As you continue to move around, and again, get about a quarter of the way around, take a look at it, see how much of the ball is illuminated, turn all the way around, see how much of the ball is illuminated, and so forth and so on, keeping yourself moving through the different phases until you return back to your original position where the moon, remember the ping pong ball is the moon, is between your sun, which is your light, and the earth, which is you. Hopefully at this point you're getting a feel for why the moon goes through different phases. And it's all about the orientation. It's all about the alignment of the sun and the earth and the moon. And here's one way of thinking about it. You can actually use what are called bisectors. So we've got this little gray thing that's the moon, and this is the earth. And what we can do is we can first of all put on the sun. So our sun is to the left of our screen, shining. And what we can do now is to create bisectors. If the sun is on the left side of our screen, then notice that the left side of our moon as well as the left side of the earth is going to be lit up. And the side that's facing away from the sun is going to be the unilluminated side. So I'm going to go ahead and I'm going to shadow those on. So notice that now our sun is on the left side of the screen, and therefore the left sides of both our moon and our earth are lit up, and the right sides are not illuminated. Now the question is, what would this moon phase look like if viewed from the earth? So what we have to do now is we have to create a line that connects the moon and the earth, and now we're going to create bisectors. So now what we see is, by creating this little bisector on the moon, we are now seeing the half of the moon that is facing the earth. We're not going to see the back side of the moon when viewed from the earth perspective. We're only going to see the side of the moon that is facing the earth. So now, imagine you're standing on the earth. What would you see? In fact, you can do that by changing the perspective here. I'm going to change the perspective here, and notice that this is what I would see if I was viewing that moon from the earth. I would see the left side lit up and the right side dark. And the question is, what is that moon phase? Well, it's going to be third quarter, last quarter. Again, last quarter is when the left side is lit up and the right side is dark. And so that's what's called the bisector method. And you can do that then. You can move your moon around. If I was looking in this perspective, again, remember that I've got my bisectors. I'm going to go ahead and go through the process again. So if the moon was in this position with respect to the earth, again, I put my sun in here. I create my bisectors. I show the shadows. So again, the left side of the moon, left side of the earth are lit up. The right sides are unilluminated. The question is, how would that moon then look when viewed from the earth? So I create my earth moon line. I create some bisectors perpendicular to that earth moon line. That's the amount of moon that I'm going to see. The side that's facing me, I'm going to be able to see it from the earth. The other side I'm not going to be able to see. And again, now if I take the earth perspective, I pretend I'm on the earth, I take a look, what do you see? You see most of the moon is actually dark, with the exception of just a little sliver on the left side that is going to be lit up when viewed from my earth. And therefore it's going to be a waning crescent phase. That's how you use the bisector method. Okay, one topic that I've really not followed up on is angular size or angular diameter. I think I introduced it in Module 2. What is angular diameter? What is angular distance? Well, let's go ahead and imagine that we're looking at the night sky. And what I want you to do is extend your arm and put your pinky up like this. Well, it turns out that your pinky, the diameter of your pinky, is about 1 degree of angular diameter. What does that mean? That means that if I take my pinky and from the horizon start stacking, one pinky on top of another pinky, I'll have to do it about 90 times until I get to my zenith. So we know that from the horizon to straight overhead, the zenith, that's 90 degrees. It turns out that I can do that 90 times with my finger. So therefore, my pinky, is about 1 degree of angular diameter. Now I want you to ask yourself this. Let's imagine that we're out in the night sky, the full moon is out. Could you cover your full moon with your pinky? Turns out you can, in fact, quite easily, because the moon's angular diameter is only about 1/2 degree. That means you could stack 180 full moons on top of each other from horizon to zenith. Very interesting. Now, what about the sun? Now, be careful if you try to do this outside. I don't want you to stare at the sun, but try to cover the sun with your pinky, and I guarantee you'll be able to do it. You can do it, in fact, quite easily because, again, the sun has an angular diameter about 1/2 degree. Isn't that interesting? So, let's think about this. How does the size of the Earth compare to the size of the moon? These are some numbers that I threw out in Module 1. The moon is about 2,000 miles in diameter. The Earth is about 8,000 miles in diameter. The moon is about 1/4 the size of the Earth. How about the sun and the Earth? How do they compare? Earth, 8,000 miles in diameter. Sun, 860,000 miles in diameter. The sun is actually more than 100 times larger. Let's just say 100 times, just between friends. So the sun is 100 times larger than the Earth. The moon is only 1/4 the size of the Earth. Now, how about their distances from the Earth? The moon is about, again, 250,000 miles. It's about 250,000 miles away from the Earth. How about the sun? The sun, 1 AU, remember, is 1 AU away. How much is 1 AU? 93 million miles. Let's just call it 100 million miles between friends. So that's the distance between the sun and the Earth. Now, how big is the sun compared to the moon? We just said that the sun is 100 times bigger than the Earth. We know the Earth is 4 times bigger than the moon. So therefore, isn't the sun 400 times bigger than the moon? You betcha. How about their distances? Isn't the sun 100 million miles away from the Earth? Isn't the moon 1/4 of a million miles away from the Earth? So therefore, isn't the sun 400 times farther away? So therefore, that explains why these two objects, which are vastly different in their actual physical size, can actually take up the same space in our sky, 1/2 degree of angular diameter. Because despite the fact that the sun is 400 times larger than the moon, it's also 400 times farther away. And therefore, just by happy circumstance, they both take up the same angular size in our sky, which is why the moon can completely block out the sun during a solar eclipse. So, now that you're learning about eclipses, you may now understand that in order to have a solar eclipse, you want to have the moon between the Earth and the sun. And you may, and then for a lunar eclipse, you want to have the Earth between the sun and the moon. But you may be asking yourself, why the heck do we not have eclipses every month then? Well, it turns out that the reason why we don't is because of the diagram on page 42 of your book. It's because the moon's orbital path is not exactly aligned. Its plane is not exactly aligned with the ecliptic. That's the plane that the Earth orbits around the sun. They're not completely lined up. The moon's orbital plane is inclined about 5 degrees with respect to the Earth's orbital plane. And that is why the moon is not always, even though if in its new moon position, it's essentially lined up between the Earth and the sun. They're not all in a straight line. The moon can either be a little bit above the plane or a little bit below the plane, and therefore the shadow that it casts into space doesn't necessarily fall on the Earth. And for a similar reason, you get sometimes during full moon phase, you don't have a lunar eclipse for the same reason. And so what I've got is a little simulation that's been running here showing you that only during particular times when the moon is pretty close to the ecliptic in either its new moon position or in its full moon position, that's when you have the possibility for eclipses. Those are called eclipse seasons. So again, it doesn't happen every month because of the tilt or the inclination of the moon's orbital plane with respect to the Earth's orbital plane. Okay, so this simulation is mainly just to make the point that all bodies will cast shadows into space. And so if we have the moon, the little moon, if I put him between the Earth and the Sun, he's going to cast a shadow. In fact, the light from the top of the Sun can get blocked by the top of the moon. As well as the light from the top of the Sun can actually get blocked by the bottom of the moon. So you're going to get a partial shadow, which is called a penumbra. You're also going to get the full shadow. That's where the top of the Sun is being blocked by the top of the moon, the bottom of the Sun is being blocked by the bottom of the moon. You get what's called the umbra. Then you have these partial shadow areas called the penumbra. And only when the umbra actually hits the Earth, then you have what's called the path of totality. So this small area on the Earth is going to see a total solar eclipse. Other areas might see a partial eclipse, but only a small area is going to get actually going to be in the path of totality. And so therefore to see a solar eclipse is a much rarer event than a lunar eclipse, because the lunar eclipse, notice the Earth casts a much larger shadow. So pretty much anybody especially because the moon is going to be much closer to the Earth than the Sun is, and so a lot of folks, anybody on the nighttime side of the Earth is essentially going to see a lunar eclipse when the moon does indeed move into the Earth's shadow. Sometimes it's just kind of a partial thing. Sometimes it's a little bit above or below the plane, so you just get a partial eclipse. Sometimes you get a completely penumbral eclipse, in which the moon is out here somewhere. But that's essentially why we have lunar and solar eclipses. It's because both the bodies cast shadows into space, and when the third body moves into the other body's shadow, that's when you get an eclipse.